Hi, good evening, everyone. We are once again in front of you after the Diwali festival. I'm thinking that is still the festive mood in India. So, welcome to this NXP Campus Connect program. And as we updated you, we are running two parallel tracks. One is the VLSI track and another one is the system engineering track. And today, the time for system engineering presentation, as we discussed in our last presentation, that this time we are going to present the more information and the deep dive on the radar technology and the radar applications in automotive segments. So today we have our expert Shashi Bhushan Rao, who is our expert in this domain. He is a technical director and did his education from BITS planning and having 20 plus of experience in the semiconductor industry. And welcome Sasi for this program. This is the Campus Connect program and most of the audience is from the college students. So try to keep the things simple so that our young innovators in the campus can understand all the jargons which you are going to present today. So over to you, Shashi.
Thank you for the introduction.
Shashi, sorry, just missed that we are going to record this, and if anyone is having any issue or concern, please raise your hand. I will wait for 2 seconds and then we'll start this recording. So after 2 seconds, Shashi, you can start your presentation.
Sure.
Thank you. Rahul, any hand raised?
No, Manish.
Okay, start. Go ahead, Shashi.
Okay, thank you, Manish, for the brief introduction. Hi, everyone. So I'm very much delighted to speak to each and every one of you for joining the webinar today. And today the topic, as you know, I'm going to speak about the automotive radar product use cases. Hope that you are able to see my screen. Okay.
Yes.
So today, below some of the stuff I'm going to speak. So first, I will go through these. These are the topics I'm going to cover today. So some of the topics I will go through first: introduction to automotive radar, and then a little bit theory about radar, and how do we implement a radar system in a system on chip in a IC, integrated circuit. Then we will move to the applications of radar and a recap and the conclusion, and then we will go for the questions. So Sudhir, can you play a brief video before we are going to the actual presentation, please? All right. So, what a fantastic video it is. Let me go through the actual presentation. By this time, you would have understand what is the topic I am going to speak about and what is the use case we are going to discuss about today. So, every technology comes up with a problem. A problem initiates an innovation in any technology, whether the innovation come from a already available technology or it can be from a altogether new technology. So here, if you see this picture, currently this is the problem statement the world facing. There is a dramatic growth use case of passenger cars, and there are undesired side effects due to this. For example, safety is a major concern. According to the European Union 2008 data, there are a huge amount of deaths on the road. And similarly, many more people are injured. And these are the direct problems. And there are derived problems out of this is a congestion and also lot of greenhouse gases and other pollution issues. Unfortunately, the most of these deaths and injuries and accidents are created as a result of human errors. In a majority of the cases, unfortunately, the problem is because of a human error. So the engineering community work
Shashi, sorry to
towards.
interrupt you,
Yes.
but your slide is not visible.
Slides are not visible.
Yes.
Oh, one second. Can you make me presenter? Hello. Are you
Shashi,
able
you are
to
a
hear?
presenter.
Yes.
You are a
One second.
presenter, but please click
Let
on
me.
show you my screen.
How about now?
It's not visible, Shashi.
How about now?
No.
No. So can you stop and share the presentation?
Sure. Are you able to see now?
Yeah.
Now we are able to see.
Oh, great.
Please click on slideshow.
Oh, sorry for
Perfect.
the issue. Okay, let's go back. If you see this slide, the problem statement is every year, according to the European Union, there is a huge amount of people are dying on the road due to the accidents. And more than that, there are a high number of injuries, and these accidents are causing. And there are a huge amount of productivity issues due to this and causing the GDP issues and many more other problems currently the world is facing. The problem is not common, not unique to Europe alone. Entire world is facing this issue. Problem is common for the entire world. Unfortunately, most of these issues are a result of human errors. According to this European report, 93% of these accidents are a result of the human error. And even this number is higher in most of the other countries. So the summary here, the problem is common across the world. The entire engineering community is currently working towards to solution for this problem. When mobility is started, when motorization is started for the mobility in 1900, around 1900, and there was now much change the way we are driving the vehicles till 2000 and even up to till 2015 or 16 timeframe. But the technology in various domains helped us to moving towards a higher level of quality ride in the mobility. Let's discuss about more in the rest of the presentation. If you see here, as a human beings, we know, right, we have various sensors to recognize everything. Our brain sees the images, and using those sensing system, our brain take decisions. Even when we are driving a system, we as a human being, we take the decisions based on our sensoring system. Similar manner, a car currently at present will have many of these sensors. Like, as I mentioned here, a camera, it can be a lidar, it can be an ultrasound, or it can be a radar. And currently a level 3 and beyond a car has all the sensors all together. So basically here we need to understand we are adding various sensors to the car, and that results and providing an information to the central processing engine inside the car to make the decision what to do next. Okay, so here I used some of the technologies here. For example, a camera is just like any other camera, but it is a very small in size. For the camera we are being using in cars, and lidar is another technology. I'm going to speak about that in next few slides. And ultrasound is another technology, and radar is a major topic we are going to discuss in next few slides. Here I mentioned level 3. So level 3 means, level 1, level 2, level 3, and level 4. That indicates the level the car reached, the vehicle reached with respect to the independent driving capability or taking the decision independently. And level 1 has a more human intervention, and level 4 is or 5 is a basically independent vehicle that can take its own decisions and drive on itself. Here I mentioned another word called sensor fusion. So basically, what a sensor fusion means. Sensor fusion means a system will have multiple sensors. It's not a single sensor. Sensor fusion is the ability to bring together inputs from multiple radars, lidars, and cameras to form a single model or image of the environment around the vehicle. The resulting model is more accurate because it balances the strengths of the different sensors. So basically, as I mentioned here, we are using different kinds of technology of sensors here, but no sensor or a technology is completely work. So I mean that each and every technology has its own merits and demerits. If you see here, radar and a vision, a camera, a lidar, ultrasonic comparison, and no technology has all features available. So basically what happens here, a radar has its own merits and demerits, and lidar has its own merits and demerits, and ultrasonic and cameras have its own technology and merits. So in generally a L3 vehicle today will have 1, 2, 3 radars and up to 5 cameras and 1 or 0 laser or lidars, and up to 12 ultrasonic devices. So radar fusion means the vehicle will have all the sensors together, and each and every sensor will work on its own, and the algorithms run on the combined result from each of the sensors. Particularly as that radar is the topic today, radar has a better against the weather and weather influences and pollution, and it is very good under poor light conditions. I mean, in the dark or night, and it has invisible integration behind the electromagnetically transparent materials. We can put the radar behind these electromagnetically transparent materials, and more than that, it's a very cost effective. If you see the compared to the LiDAR, the radar is a very cost effective technology. And here it's a comprehensive comparison between the various technologies. Ultrasonic is a very cheap, but the disadvantage is very imprecise. You know, it can detect objects in the range of few meters. It is not enough because the vehicles run at very high speed. So even the approaching target vehicle or the car we are driving are in a high speeds. So a few meters is not enough to take a decision. So LiDAR is very good with respect to the three-dimensional resolution and 3D imaging of the environment, but it is a very expensive as on today. So it uses the light waves for the to detect the objects, but it's a very expensive. And the radar has a good range, moderate range of 30 to 200 meters, and it is very affordable and very good under bad with snow and tunnels. So under the snow and tunnel conditions, radar doesn't work properly. Cameras have a good resolution range up to 500 meters. It's affordable, but you know it needs a good lighting conditions. So this is the drawback. And VTX is another technology. It can work up to 1 kilometer, but the problem is it doesn't need a line of sight, but requires a huge infrastructure to support the VTX technology. So based on these advantages and disadvantages, the sensor fusion strategy uses one or more types of these sensors and chosen for different functions. This is how the car utilizes the various sensors to make the object, to meet the object. So this is the history of radar. Radar is a pretty old technology. It is somewhere from 1904. Radar being used in various things. Initially, radar detection and ranging, the short is radar, being used by US Army, and later this was migrated to various technologies like, you know, air traffic control and marine navigation and meteorology. Later in 1970s, the signal processing and the solid state computers are arrived. As the technology is been moving towards the solid state technology, we could able to integrate the radar into the system on chip. That is where the engineering community started using the radar inside the automotive vehicles. Currently, because CMOS technology, we could able to integrate radio frequency RF, I mean to transmit the electromagnetic waves and receive the electromagnetic waves. That is the technology behind the radar. And the digital signal processing and the digital logic, entire thing we can integrate into a single chip because of this CMOS technology. So RF CMOS enable us to integrate each and every technology I have spoken about and make this possible to integrate into a tiny devices so that we can install in the cars. This not only allow us to reduce the power consumption of the chip, and also it gave the tiny devices. Right? you could able to integrate entire system into a single chip, which is almost a size of your thumb. So basically, what is the technology behind the radar? Okay, so basically radar acronym stands for radio detection and ranging. Radar is a device to detect the objects using electromagnetic signals. There will be a transmitter and a receiver as shown here. The transmitter sends the electromagnetic signals, and it will hit an object. It can be a moving object or a stationary object, and the signal will be reflected back, and the receiving antenna detect that signal and then the signal will be processed further to detect the distance of the object and angle of the object and other parameters of the object. Okay, so this is the technology behind. This technology being used in military and air traffic control since last 100 years, and since last 30-40 years we are started using. But technology in CMOS and very large scale integrated technology VLSI made this possible to integrate radar into the CMOS chips. And here there are various kinds of radar, and I discussed it here in this slide. So basically, there are high-level pulsed radar and continuous waveform radars. And pulsed radars are basically, they generate a single pulses like this, as shown here. And the pulse will be transmitted, and it will be returned back after hitting the object, and the delay will be measured to measure the distance of the object. Okay, this is the pulsed radar. And the frequency modulated continuous wave radar is a form of continuous wave radar. And FMCW, frequency modulated continuous wave radar, is a radar technology where we send the electromagnetic wave continuously, but it is a modulated in frequency domain. A frequency modulated continuous wave radar system with its continuous measuring signals is capable of good range resolution, often as fine as 0.5 meters. So we can able to get a very good resolution. A pulsed radar system, on the other hand, is not quite as good on range resolution. It typically suffers a large blind spot in front of the radar of 50 meters or more. The resolution is not good in pulsed radars. And continuous wave radar, that is a CW radar of pulsed radar, frequency modulated radar, is a special type of radar sensor which radiates continuous transmission power like a simple continuous wave radar. In contrast to the FMCW radar can change its operating frequency during the measurement. That is, the transmission signal is modulated in frequency, so that it can be modulated in phase as well. So FMCW radar can modulate the frequency or phase, and that gives a better resolution. So that is the reason majority of the automotive radars today are FMCW radars. And this is how the frequency modulated continuous wave radar works. If we see the transmitted signal here, the frequency is modulated, is a low frequency here, and it is a high frequency here. The frequency is modulated continuously. A transmitted pulse will send like this. The frequencies keep on increasing, and the received signal will be received, and it will measure the round trip delay between these pulses, and that will tell us how much distance the specific object is. FMCW operation is independent of the speed or a direction of the travel of the target, and it gives a very high precision to finding the object, and it is a less complex, safer, and lower in cost compared to the pulse systems. Of course, the consumption of power is a little high compared to the pulse systems, because we are continuously modulating the frequency and sending the modulated electromagnetic wave, whereas in pulse systems, we will burst the signals for a short duration. But still, because of the resolution and smaller in size and implementation feasibilities, we go for the FMCW radar in the industry. Here, we are going to the next level of details. Earlier we know that there is a antenna, transmitting antenna. It sends the electromagnetic waves, and the signal is hit the object. These are the objects here, and the signal reflected back, and the data received signal is captured by the receiving antenna, and that is a pure analog signal, and we need some digital to analog to digital converters here, ADCs, in a baseband domain. And because it's an analog signal, after that we need a digital signal processing tools to process this analog to digital converted signal. Then the algorithms, Fourier FFTs, run here as a part of the digital signal processing. Then the object will be detected. Once the object is detected, and the next level of action will be taken care by the central processing units, whether we need to continuously track the object or to take some specific decision. For example, if I want to take a lane change, for example, whether the vehicle needs to take decision whether to change the lane safely now or later, right? It detects an object and around it. So if it is not safe to take the lane change, it needs to track that object till the safe change movement occurs. So, radar frequencies, as I mentioned here, radar works with electromagnetic waves, but electromagnetic spectrum been used by many applications. So earlier radar, automotive radar uses the 24 gigahertz technology, but that is a little bulky because the wavelength is high, because the frequency is less here. We will discuss more on this later. And as on now, you just remember 24 gigahertz radar been used earlier, and nowadays industry is moving towards the 77 to 79 gigahertz range for the better resolution and to integrate in a smaller packages. And rest of the spectrum being used for various other applications like FM wave, FM radio, and Wi-Fi and other technologies. Here we can discuss more. So the main aim of the sensors in any vehicle is to detect the cars around us and seeing the pedestrians and bicycles. And similarly, we go for the full 360 degrees surround you. Many of the luxury segment cars, mid-end luxury segment cars currently have all these capabilities. We could able to see what's happening around the car. And similarly, we can 3D mapping of the environment as well, even with higher level of capabilities in the radar. So, but as I mentioned earlier, the 24 gigahertz radar nowadays not being used because it's a bulky and it consumes very high power, and it uses the silicon and germanium technology, and it's a low resolution as well. While we are moving towards the right, the 77 gigahertz radar uses the RF CMOS, and which consumes CMOS, very well. It consumes less power, and it is feasible to integrate radio frequency antennas and analog into a single chip, and it's a very tiny in size, and it provides high resolution. On top of that, the signal processing, which we measures in terms of floating point operations, gigaflops. Gigaflops means giga floating point operations, which is feasible nowadays because of the technology available and digital signal processing capabilities feasible nowadays. It is feasible to achieve to do the digital signal processing greater than about 350 gigaflops of operations for the 3D image processing radars. So the ultimate goal for any company like NXP works in radar system, we need to integrate entire system into a single chip solution. I want to show here, you see this tiny chip. The entire solution will go into a tiny chip like this using RF CMOS technology. The chip itself will tell you how much tiny it is, but a lot of functions it can handle, and it consumes very, very less power. And so typically a radar system consists of a transmitter. So it has a power amplifier signal and generated here using a waveform generator. And this power amplifier sends the signal towards the objects, and a waveguide, it's a facilitate the transmitted signal to a specific direction, and the antenna, it transfer the transmitted energy to the space around the antenna, and the receiver use it for detection of the signal, received signal, the echo, and a processing unit uses the captured signal processed further to detect the object and track the object and to take further action by the car or vehicle. Typically, based on the applications, we use various kinds of radars. In generally, three kinds of radars are there. There are short-range radars and medium-range radars and long-range radars. So, for example, you think yourself, if I want to park, we need not require a long-range radar. A short-range radar is enough to parking a vehicle, because the vehicle moves very slow, and it needs to care about only the objects about up to 10-20 meters range, not beyond. So if it is a front side radar where in a cruise control system where the vehicle runs up to 150 200 kilometers speed, definitely we need to get a target range of 250 to 300 meters and above, where long range radars are useful. For medium range radars, typically for surround view and what is happening side view of the car and what is happening just around the car, and a medium range radar will be helpful. So typically a radar system can be partitioned into three technologies. One is radio frequency domain or RF domain, and another is a baseband domain, and another is a digital domain. So all these technologies integrated into a single tiny chip and function together. RF domain specifically will have the, as I mentioned earlier here, the transmitter, waveguide, antenna, receiver will be part of these PLLs, phase locked loops for the frequency generation, and all these part of this radio frequency domain. It means completely analog domain. And next, we need to convert the received analog signal into digital domain for the processing by signal processing tools, SPTs, digital signal processing tools, DSPTs, that is called BB domain, baseband domain. And once the signal processing is done, we will move towards the complete digital domains, where our central processing units like CPUs like ARM or MIPS or the RISC-V, any of these CPUs will work there, and even our RAMs and DRAMs, flash will work there in the digital domain. And this is a typical radar system on chip. If you see here, there is a radar processing platform here where the entire analog sits here, and there is a digital processing domain where central processing units sit here, and this is the bus to communicate with various peripherals here. The key point in this SoC block diagram, system on chip block diagram, there are various technologies work together to meet the automotive applications. You know, by just integrating a radar processing platform and a CPU is not enough. There are other things we need to care about. Here, there is a security engine. These blue boxes will take care about security of the chip, hence the security of the vehicle, so that an intruder cannot hack the car or the vehicle. Similarly, there is a safety engine blocks here will take care about the safety of the chip and safety of the system, hence the safety of the vehicle. So security and safety looks interchangeable, but they are altogether two different technologies here. Security will help the system not to eradicated by the intruders so that nobody can hack the car or the vehicle. And safety, whenever a fault occurs, and safely move the vehicle system into a safe mode so that the issue doesn't happen. That is the safety. So currently, you know, the radar and the power architecture here, whatever I mentioned, central processing engines take care about the functionality of the radar system, but security and safety help the system robust. And typical automotive radar processing flow is mentioned here. So here I have mentioned here, you know, the receiving signal will come from the antenna, and from there what will happen is a monolithic microwave IC, an integrated circuit using in high frequency application such as mobile phones and radars will use the MMIC technology, and from there the signal processing also will be taken care by that MMIC technology, and then signal analysis and detection and tracking is being done. These are the various phases, and even safety and security is part of this high performance MCU. And this is another version of the topic we just discussed. You know, the ramp generator and synthesizer and a power amplifier will generate the electromagnetic wave here, and electromagnetic wave will be transmitted to the object here somewhere around in the space, and the signal will be echoed back to the receiver, and the receiver will receive the signal, and it is amplified and mixed up with the transmitted signal, and this is a low noise amplifier, and the amplified signal will be mixed up with the transmitted signal, and the resultant difference will be again amplified and given it to the ADC. And you know, that will be further signal processed, and the hardware accelerators are typically useful to provide the data to the signal processors in high speed with low latency. Otherwise, the signal processors won't get the data from the memories quickly. And once the digital signal processor analyzes this data, and it will provide the write back the data to the memory, and CPUs will read the data from the memory, and from where it will further process the data. You know, the data can be further transmitted to the rest of the cloud or another central processing unit via Ethernet, or it can utilize itself for taking the decision. Here, I little bit more details I discussed here. You know, as we discussed, the analog to digital converter will provide the data to the signal processing tools, and And once processing is done, the results will be saved to the internal memory. It can be SRAM or any memory, and the CPU will read the result, and it can be sent it to the cloud for further processing, or it can take, if it is an edge device, means the sensor itself is able to take the decision, then it can take the decision in the vehicle itself. And the same system here, it's mentioned here in a more details. This is a CPU and radar processing platform, and connectivity and safety and security is handled by the multiple subblocks. So earlier I mentioned about the safety. A little bit speaks about safety. You know, even after meeting the technology, means we could able to detect the objects precisely, and we can able to track the device objects precisely, but at the same time the safety of the system and security of the system also important. You know, there is a automotive safety integrity level, ASIL in short, is there. So the ASIL describes about automotive safety, so that whenever there is an issue happens, what are the steps needs to be taken. So this is the ISO 26262, a safety standard, speaks about the level of safety standard we need to ensure while designing the products, system on chip ICs. The safety standards start from the requirement specification, design specification, and physical design flows and integration, RTL language writing, and even software coding. Entire thing need to various levels of safety standards we need to meet in order to get this certification. So there are 4 levels of certifications. Level A with a very minimal, and level D is a extremely high safety standard. So autonomous cars requires level D standards. That means 99% of faults the system should be able to detect on its own, and it should safely land without any catastrophe. So can you please play these 2 videos for me?
For more than half a century, Mercedes-Benz engineers have been answering the same question in newer, more imaginative ways. How can we make driving safer and more enjoyable? In the 1950s, the answer was the first crumple zone and the power of fuel injection. In the 1980s, dual front airbags and the handling precision of the multi-link suspension. Our latest response leaps further ahead than you ever imagined possible. Introducing Intelligent Drive. It's more than a new feature or even a new system. It's a new generation of breakthroughs to help make driving safer and easier. What if your car could actually see what's ahead and respond right in the moment? A radar sensor and advanced cameras, including a new stereoscopic camera in the windshield, allow Intelligent Drive to recognize objects 360 degrees around the vehicle. Radar sensors give it foresight. Long, short, and multi-range radar scan the environment in front of the car, behind it, and out from the rear corners. The intelligence comes from insight. Advanced computing power interprets what it sees, determines the best response, and springs into action faster than humanly possible. The systems of Intelligent Drive can recognize a pedestrian entering your path, vehicles ahead slowing to a stop, and even cross traffic at a nearby intersection. The moment it does, it lets you know. As soon as you brake, even if it's too lightly, Intelligent Drive can increase it to the precise amount needed, even applying full braking power. And if you don't respond, it can initiate braking on its own, all to help reduce the chances or severity of an accident. With Intelligent Drive, driving isn't just safer, it's easier to enjoy. Imagine cruise control that adapts your speed to the flow of traffic and your steering to the curve of the highway. Imagine your car seeing bumps in the road and responding before you can feel them. With Intelligent Drive, it's no longer beyond imagination. It's here. Changing the course of automotive history starts by looking into the future and looking out for yours.
Next slide, please. Next video, please. All right. So let's move on to next slides here. As we have seen so far in the past few slides, these are the various places we can use the radar technology. It can be used for blind spot detection and lane changing assist, rare cross traffic alert, and what is happening behind the car, and rare collision avoidance and parking assistance, front collision, adaptive cruise control, auto emergency, and rest of the stuff. The completely 360 degrees assist. The car is now capable of seeing everything around it and react accordingly. And currently, the industry is moving towards complete autonomous. So, as I mentioned earlier, currently we are at the level 3 automation for the vehicles. And in near future, we are moving towards level 4, that is a self-driving vehicles or autonomous vehicles. Here, if you see here, the level 1, the driver needs to assist him a lot, and most of the functionality is done by the driver, and very less being done by the vehicle. And if you're moving one after the other, in the level 4, the vehicle itself take its own decision, and there is no need of the human intervention. So all this feasible with the technologies currently available. So the level of integration into the automotive chips like radio frequency, analog, the digital and digital signal processing, integration into a single chip made this all feasible. But apart from that, the integration of safety and security technologies also enable this. And on top of that, the amount of computing resources available today make the cars take these decisions on their own. And so I would like to recap one more time here. So today we discussed here about introduction to automotive radar, fundamentals of radar and types of radar, radar implementation on a single chip, that is a system on chip, and applications of radar in driving assistance. So we need to see that what are all the areas of focus in order to work on a technology like this. So NXP is a world leader in automotives, in even automotive radars, and we develop the system on chips with all these technologies. So basically, in order to get hold on this technology, it is a combination of multiple technologies to stitch together to get a single system on chip. For example, to make an autonomous vehicle, the radar fusion is one of the most important stuff because single sensor technology won't meet the requirements. And digital signal processing, amount of processing required to process the receiving analog signal is another technology. And fundamentals of radar in the analog domain is another technology. And more than that, we need to design a chip to meet the power requirements given by the customers. So nowadays, the chips needs to operate in terms of milliwatts or microwatts rather than tens of hundreds of watts. That means we need to be very good and learn low power system on chip design in order to meet the requirements for the advanced driving assistance systems. Not only that, so currently artificial intelligence and machine learning is booming. In order to make the system autonomous, in order to make the vehicle autonomous, artificial intelligence and machine learning algorithms need to run by the signal processing engines. But the problem is, in order to run the artificial intelligence machine learning algorithms on the receiving data, we need to have a powerful processing engines as well. Similarly, we need to have a powerful memory technologies as well. The problem is we cannot able to send the data generated by a vehicle to the cloud due to various reasons. Number one is a bandwidth limitation. Each and every car generates terabytes or gigabytes of data every day. We can't able to send this data to the cloud for the processing. We need to process the entire data within the car, I mean in the edge itself. That is called edge processing. Means the sensor itself should be able to process its data generated, called edge processing technology. This is also one of the technology required. Another technology, if you want to store the received data, you need to have a huge amount of RAM inside the system on chip. Similar, at the same time, the CPU needs to read this data, the signal processing engine needs to read the data and processing and write back the result. This is again huge latency we could not able to do because of the amount of data we are receiving, and the decision should be taken immediately. Not only that, when we are writing and reading the data into the SRAM, it consumes a lot of power as well. In order to meet the robust latencies and performance requirements and low power, we need to do the computations within the memory itself. That is called in-memory computing. So as I mentioned here, a lot of technologies, by combining each and every technology together, a single system on chip will be generated for the automotive industry and automotive vehicles. So this is as a closing note, I can say that it's a tremendous technology and it has a highly deterministic and future-oriented technology and industry by mixing all these things. And hope you guys are seeing this topic as a very interesting, and thank you all for joining the meeting today. Manish, I am done.
Yeah, Sasi, thank you. Rahul, if any questions from the attendees, maybe first stop the recording.
Are anyways using a long range radar. Do we really need short range radar? Can't we use long range radar for all the presentation and the hard work that you have put in? And thanks to all the attendees for sending in so many questions. We may not have been able to answer all of them. You may, if you have any specific questions, you may post it on LinkedIn, and we'll get the relevant experts to answer these questions. If it is radar based, then of course we'll pass it on to Sasi, so Sasi can look at the questions and answer them on LinkedIn itself. So that would be the end of this session. Next session would be on VLSI track, and it would be, I think, 1st of December. The topic is analog is on analog design, and this has been one of the most asked about question from a lot of the attendees. Now we're going to present on analog design. So definitely for 1st of December, and I promise it would be a very helpful session for the people who want to make their careers out in analog. So with that, we'll end this session. Thanks again to all the participants and presenters, Sasi. And we look forward to hearing back from you. And stay tuned for the future presentations on the NXP Campus Connect. Thanks a lot, guys.
Thank you all. Bye.